let's just continue from here. Alright, so let me get a blank screen and let's go through what it's supposed to look like. So what we're supposed to be having, KC being equal to what? So KC is equal to what?
You want the letter format or you just want the numbers?
I mean the overall format itself.
I have C raised to the first power times B squared divided by A squared times B cubed. And then we punch in the, substitute.
So the concentration of the products, right? And then we have concentration D squared. Alright. And then we divide that by A, concentration of A, what squared?
Yes, sir.
And
times B cubed.
okay. And that is going to be equal to 0.3 times 0.2 all squared divided by 0.5 squared times, that would be 0.8, right?
Cube, yes.
Cubed. Okay. And the answer we got, so let me just do over my answer. Probably it's a sickness, you know? Probably it's a flu. Let me square it. That is that. Okay. Let me actually not do that. 0.3. Alright, so that is that. So you guys seem like everything is fine though, so everything should be fine. So it's just a matter of calculating on whether or not I calculated wrong earlier. 0.0937. That's what you guys got?
Yes, sir, but I round up. So 0.094.
I'm not sure about rounding and chemistry, you know, but alright. So 0.09 is pretty fine actually. It's pretty fine. But if you want to be more specific, I tend to go this far. Alright, so that is that. Are there going to be any units of KC here?
Mole per dm cube.
Repeat?
Moles per dm cube.
So I was saying that the unit is mole per... interesting. Alright, so the unit is mole per dm cube. So remember, this is mole per dm cube. Remember these concentrations. Let's look at this. Right? So we're gonna have we know that the capital M is a mole per dm cube, right?
Yes, sir.
So if we have mole per dm cube times mole per dm cube squared on the numerator, what do we get? This would be cubed, right?
Yes, sir.
Alright. And then on the denominator, we have squared and cubed. So what would that give us?
M to the fifth.
M to the fifth power. Alright. To the fifth power. Right? And then when we cancel now, if we cancel 3, right, that third power and that fifth power. Hold on, I'm not knowing. Okay, the pen is deciding to write wherever it wants to write. Alright, so we have that there. So if we cancel this, so it should leave 2, right?
Sir, would it be -2 though?
I mean, it would become negative when it goes onto the top, right? When it goes over 1, right? Because we would have to invert it. So it would be mole per dm cubed all squared, right? and then you would have to make that the negative values, right, or invert the values. What do I mean by that? That doesn't make any sense. What do I mean by that? Right? It means that it would be mole -2 dm6. Right? So we have something like that. So the Kc does have units per se. It doesn't have to have the same type of units as concentration. But question, Kc have units? Let me ask you a question. Does the Kc itself have a unit? Do we write units for Kc?
Sir, based on what I'm seeing on the screen, I'm gonna go with a no.
No? LOL. Alright. Kc does have units, by the way, but Kp is the one that tends to not have a reported unit. Alright? Tends to be unitless. But Kc does have units. Alright? Overall, it tends to be moles per dm cube. Right? But when you work out the units of K, then that's what you get. Alright?
So am I supposed to use moles per dm cube or that?
Or what? The large M, you can use a large M if you want. Right? The capital M. But we use mole per dm cube in the Caribbean. Mostly.
So why I got you add that?
I mean, because the thing is that if you just use the capital M, you won't be able to get these quantities, specifically the -2 and the 6, properly. So we want to show everything properly. Because when using the large M, we're just assuming that it's mole per dm cube. Because it's just a flat unit. So that's why when you're writing the equations and everything, you're always writing all the units so you can see where units cancel, etc., and get your final unit at the end of the day. At the end of the day. Alright? So, let's move on. Dalton's law of partial pressures. According to Dalton's law, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the individual gases. Interesting, isn't it? So, if a gas mixture contains n different gases, then the total pressure rather is given by this. So P total is the sum of every other partial pressure. Does this make sense?
Yes, sir.
So if A exists and only gas A exists within a chamber, then the overall pressure exerted within the chamber is gas A. But if gas A and gas B exist in a chamber, then the total pressure is the sum of gas A and gas B. That makes sense, right?
Yes, sir.
Yeah, so the total pressure is the sum of all the different pressures, right? So that is basically what he's saying. It was so revolutionary to figure out something so painfully obvious, right? But it probably wasn't painfully obvious at the time. So consider this, right? Consider this example before I just go and ask you to calculate the Kp of something. Alright, so consider this here. So we have the sulfur dioxide plus oxygen to give us our sulfur trioxide in this case. All in gaseous phase, is a homogeneous phase. Alright, so given that an equilibrium, right? Well, at equilibrium, the pressure of the sulfur dioxide here is at 0.30, right? So the partial pressure would be 0.30 atmospheres, for oxygen 0.20 atmospheres, and for sulfur trioxide 0.40 atmospheres. So calculate the Kp. So first we have to write our balance reaction, then we apply Dalton's law, then we substitute the given values per se. So the overall total pressure is 0.90. Alright? So we just have that. But what do we do with 0.90 though? What do we use for that? Why do we find the sum of all the gases? Can anybody give me a use for defining the total pressure of everything in the system? In this case, it's not really necessary because you're given all the pressures. But in the case where you have total pressure and then some other gases they did not give you the pressures, you can always transpose the equation, right? Dalton's law, in order to find the missing pressure, right? So we tend to use it to find those type of stuff. Right? And some questions it may tell you that gas A, right, its pressure is at twice the magnitude of gas B, etc., etc. The total pressure exerted is 0 point something something atmospheres, and then you're just supposed to figure it out. Right? So we tend to have that information, especially for finding variables. But in this case, we have all the variables we need, and we don't technically need it. Right? You guys can ignore this specific area right here, number 4, right, and then move on to writing the expression Kp and then finding the value for Kp there, right? So it's generally the same thing, products over reactants, but in this case it's pressure. Make sense?
Yes, sir.
All right, where is everybody else? Everybody else fine? I'm just saying that you can ignore number 4 because those equations and those things you may use them soon. Probably not soon, but yeah, I'm not gonna use it for now, and you won't need it. So you just need to understand those concepts, and you should be fine. So look, another gift. Wow. Now, question 1: consider the reaction here, the Haber process. Given that at the equilibrium, the partial pressure of nitrogen gas is 1.5 atmospheres, the partial pressure of hydrogen gas is 2.0 atmospheres, and the partial pressure of ammonia is 3.5 atmospheres. Calculate the Kp. Notice that these are rather easy questions. It's just to get you to understand the concept. I can create questions that, don't look too right. And if you want those questions, just let me know. But yeah, just make it really easy and simple. Everything is there given to you, so all I have to do is apply Kp, and it should be good. So I'm going to give you the time to just go through number 1, and you can attempt number 2 and 3 on your own. I already have an answer for number 1, so just let me know what your answer is when you get it. Give me a moment, guys. Okay. Sorry about that. Just give me a moment. Hello, yeah. Is everything good? Is everything well? Have you guys finished? Not the silence.
Yes, sir. It's just for confirmation.
Interesting. Okay. Alright, so let's have a look at this. Let me go to the chat here to see, because okay, so our answers here so far are what? 65.3. That's a cute value. That value is really cute. Alright. Ooh, we're having different. Okay, alright, hold on. Hold on. We're having an entire spectrum of values. Alright, so what would KP be here in this case? KP would be what? Partial pressure of ammonia divided by the partial bracket it, right? Ammonia itself, let me say ammonia is brought to the power of 2, right? The partial pressure of the nitrogen gas, right, brought to no power, the power of 1 technically, and then not plus. What am I doing? Come on now. All right, times the partial pressure of the hydrogen gas, right, brought to the power of 3. Really simple things, right? I'm concerned about how we get different answers, but we'll work it out real soon. So I'm just gonna wait a little bit to see what we got, what everybody got. Anybody else got any other answers? I just wrote that there to make sure that, if there were any mistakes, there were any mistakes in the thing. Okay, so you got, all right. So those look like fairly close values. I have to say fairly close because I want to be nice. The values don't look so close, but let's look at this. Let's use over here. So it's gonna be what, 3.5 brought to the second pole over 1.5 brought to the first pole times 2.0 brought to the third pole. And what is the answer that we get? Let me get the calculator and see what happens. So 3.5 squared. Wait, let me do it differently. So we're having 3.5 squared divided by, let me use brackets to make sure, 1.5 times 2.0 cubed, basically. All right. Well, no, the bracket shouldn't be there. All right, that looks fine. So the answer is 1.02. All right. So everybody's fine so far? Everybody's good so far? Just let me know. Drop a 1 in the chat if you're ready to move on. It's actually 1.2, I see. So Shanique, I'm not sure, you probably have to recalculate. And the person was 1.042. It looks interesting, but I'm wondering how is it that much off? Cause like, if the value is really off, that actually scares me less than having a value that's so close. Alright, so let's reevaluate, right? And it should be fine. Okay, so Le Chatelier's principle. So Le Chatelier's principle now. Let's get into the good stuff. No, this is a lot of memorization, right? So Le Chatelier's principle states, let me just check something real quick. Okay. It states that if a system at equilibrium is subjected to a change in temperature, pressure, concentration of reactants or products, or the number of moles of reactants or products, the system will shift its position to counteract the effect of the disturbance and restore equilibrium. What does that mean? What does that mean? Anybody? Any brave individual? What does that mean? Everybody's scared to say something? What is Le Chatelier's principle telling us? Okay, so nobody wants to tell me what Le Chatelier's principle is telling us. Alright. So with temperature, right, the effect is, right, changes in temperature can affect the equilibrium position, right, of an exothermic or endothermic reaction. Right, so if the temperature of the system increases, right, the equilibrium position will shift in the direction that absorbs heat to counteract the increase in temperature. So for an exothermic reaction, the equilibrium will shift to the left, right, to consume excess heat. Conversely, for an endothermic reaction, the equilibrium will shift to the right to absorb the additional heat. Make sense? Does anybody need an explanation for this? Anybody needs like an equation, an explanation? So for an
Sure.
Sure. LOL. So for an exothermic reaction, right, the equilibrium will shift to the left to consume the excess heat. So if we have A in equilibrium with B, and our enthalpy change is what? Negative, because it's exothermic. That is not a B. Right? Our equilibrium will shift to the left to actually absorb some of the heat, to actually consume some of the heat. So the equilibrium will shift to the left, meaning it will favor the reverse reaction, the endothermic reaction. Right? So if we have an exothermic reaction and we continue to increase the heat, then it will actually favor the reverse reaction. The equilibrium will shift to the left to decrease the temperature. Make sense?
Yes, sir.
Alright. And conversely for endothermic reaction, so let me make it endothermic now, positive value for our delta H. Right? So if this was endothermic and it continues to become cold in equilibrium, we will shift our reaction, right, to the right. Well, I mean, it will shift to the left, right? So I'm not going to say it will shift to the right. It will shift to the left, rather, right? In favor of the exothermic, right? So what you guys need to know is that if you have a temperature reaction, right, a type of thermic reaction, right, if the forward reaction is exothermic, then the reverse reaction is endothermic. Because if you are creating heat in the process, that means that the reverse should be you are absorbing heat in the process. Right? So it's really simple like that. Alright? So if you're talking about an endothermic reaction now, the equilibrium will shift to the right to absorb additional heat. Right? So in the case that you're increasing, give me a moment. in the case that you're increasing the temperature, right? Let's say that, the forward reaction here, A to B is endothermic, right? If you're going to be increasing the heat, it's going to be shifting to the right, right? So it's going to be trying to absorb that additional heat specifically, right? If you're going to be increasing the heat, then it will shift to the left, right? Vice versa for exothermic reactions. For exothermic reactions, you just switch the positions, right? So for exothermic reactions, if you increase heat, it actually moves to the left. And if you decrease heat, it moves to the right. Right? So what we're trying to do is stabilize temperature, right? And that's what Le Chatelet's principle is all about. If there's a change in something, equilibrium position will shift towards a direction that minimizes the change, right? Are there any questions? All right. So that the information is here, endothermic and exothermic reactions is just a subset of what I just explained. Right? For concentration now, changes in concentration of reactants and products can affect the equilibrium position. So if the concentration of reactants is increased, right, or the reaction or the product is removed, the equilibrium will shift in the direction that consumes the added reactants or that produces more of the removed product. Right? Conversely, if the concentration of the product is increased, right, or the reactants are removed, then the equilibrium will shift in the direction that consumes the added product and it produces more of the removed reactant. Right? So if we have let's say Haber process. Right? So in the Haber process specifically, our product is ammonia, right? Our product is ammonia. So industrially, we'll be collecting ammonia. As we remove ammonia from the system, right, it pushes the equilibrium in this direction to replenish the concentration of ammonia. Right? That's what happens. Right? And while the concentration of reactants start going down, let's say that if the concentration of nitrogen, well, it would be the partial pressure in this case, but let's say the concentration of nitrogen decreases, right? Then we will actually move in this direction to replenish nitrogen. You guys understanding? It's giving no. Are you guys fine?
No, sir. Can you repeat that, please?
So what we're talking about in concentration is that if we have the increase or decrease in something, right? Remember that the concentration must remain constant, right? Right?
Yes, sir.
So let's say that all of these have the concentration of 1, right? They're all in equilibrium, lovely, right? If this becomes 0.5, because it should be at 1, the equilibrium position will shift to produce more ammonia to get it back at 1. Right? And it will shift to get it back to 1. And then there will be no more shifting. It is now back in equilibrium. Right? If the concentration of, let's say, nitrogen, as I was talking about earlier, has now decreased to 0.2, the equilibrium position will shift to the left to replenish the reactants. Because that's what the concentration is saying. The equilibrium will shift to whatever this direction to minimize the change. So what we're saying, at equilibrium, everything should be fine, right? If there's a change, then the equilibrium position will move to minimize the change, right? To bring it back to what it eventually was, and then it will restore equilibrium. It's all of Le Chatelet's principle is all about the restoration of chemical equilibrium, right? Same thing if we increase the product of the reactant, well, not the products of the reactants, but like the concentration of the reactants, right? Let's say nitrogen is now 2, the equilibrium position will actually move to diminish that amount of nitrogen, producing way more products to decrease the amount of nitrogen back to 1. So if you guys are following, all it's doing is moving to make sure that everything is as it was at equilibrium. And that is what Le Chatelier's principle is all about. This is Le Chatelier's principle in concentration. So the equilibrium will shift in the direction that satisfies the change, or that minimizes the change to bring it back to equilibrium. So if you have an increase on one side, we will shift to the other side. If you have a decrease on one side, we'll shift to that side that has the decrease, right? So it's gonna continue shifting, right, to benefit the entire equilibrium. Make sense?
Yes, sir.
Is there anybody that it still doesn't make sense to? Because no. So it's all about doing that, right? So it's all about replenishing the equilibrium. Having a look at the pressure as well, right? So pressure is in relation to gases. So if the pressure of a system is increased, then the equilibrium will shift in the direction that reduces the total number of moles of gas to counteract the increase in pressure. So let's look at something like, let's say we have A, and we're going to be, well, let's say that A plus, oh, give me a moment. I think my laptop is most definitely dying. Give me a moment, let me plug it in. Alright, so it's fine now. So if we have something like this, and let's say, let me remove that actually. Let's say A plus 2B gives us, what would it give us? Just using arbitrary things though, let's say that it gives us 3C. Right? So we're looking at this. So we're talking about the gaseous mixture now. Why do my arrows look like that? Okay, they're gonna look like that. Alright, so let's look at this now. If we're going to have an increase in pressure, we're going to favor the least amount of moles. Right? So if we have an increase in pressure in a gaseous system, we're going to favor the least amount of moles. So let me change this actually, because this is not going to be helpful. Let's use this. This is going to be helpful. So let's say that you want to create a product for C. You're going to have to do it at a very, well, not a very, but at a low pressure. Because if you increase the pressure on the system, it will shift in this direction. Alright, it will shift to the left. And we will favor the production of the reactants more so than production of the products. Right? So that's what the pressure is talking about. Right? So if we increase the pressure on our system, we will favor the side of the reaction with the least amount of moles. This appears on your Unit 1 past papers. It appears almost everywhere. Right? Give me one moment, please.
How about in the extension? Is it? You use the extension?
So let's have a look at this, right? So everybody understanding this so far?
Yes, sir, I am.
So we just favor the side with the least amount of moles. So that's why when we look at things like like the Haber process, we have to do it on a high pressure, right? So we tend to have something like N2 plus 3H2 would give us generally 2 moles of ammonia. Alright? Well, ammonia is H3. Alright? So if we're looking at something like this, we have to do it under high pressure, right, to favor the production of ammonia. Following? All right. So chemical equilibrium is all about, it's literally chemical engineering, right? So it's all about being able to move everything to your will, right? To make sure that you get what you want and to manipulate the chemicals into doing what you want them to do, right? So it's something like that. Why I always make reference to Haber process is because that's what your syllabus wants, right? It's in your syllabus, it's written right there. Alright, so the number of moles is really the same thing here, so it's just additional information. Alright, so Le Chatelier's principle is of utmost importance in chemistry for several reasons, right? So the predictive power, right, that Le Chatelier's principle gives you, right, is unparalleled in chemistry. Alright, once you understand Le Chatelier's principle specifically and understand how external conditions can affect your chemical system, you can predict anything. Right? So chemical reactions will not be able to fool you. You can predict anything. Right? You can predict any eventual outcome of the chemical reactions under any other different conditions. Under any conditions. You will know what will come out. Right? So understanding the Chatelier's principle like that. Understanding chemical equilibria is also important. Right? So by understanding the Chatelier's principle, we gain a deeper understanding of dynamic nature of chemical equilibria. Right, so when we start talking about the re-establishment of different changes within redox equilibria and acid-base equilibria, we'll be able to understand that or appreciate that a little bit more. Right, another thing is the optimization of industrial chemical processes. Right, majority of our industrial processes that produces all these products that we know and love, right, are all governed by Le Chatelier's principle. Because they're all governed in such a way to produce the product, right, at the most efficient way, right? So if we have an endothermic process, right, we tend to use Le Chatelier's principle in order to actually favor our product, right? We tend to move reactions to favor the products that we want them to produce, right? So product or process optimization is one important thing, especially when it comes to chemical manufacturing, right? And the environmental impact as well, right? So everything in life itself, in the world itself, really occurs through chemical systems. You cannot avoid the chemistry. It's always there, right? You yourself is chemistry. Alright, understanding how changes in external conditions influence chemical equilibria is essential for assessing the environmental impact of chemical processes, right? By predicting how changes in reaction conditions affect the production of pollutants or greenhouse gases, right? So we are able actually to develop different strategies to minimize environmental harm, etc., right? So there are multiple processes that we can look at. And I know that you guys would have studied RDA in, like, I don't know if you guys do Caribbean studies or communication studies, right? But you guys would have looked at different processes such as ocean acidification and those type of things, right? How climate change affects that. If we increase the temperature of a system, right, the reaction will favor something, right? It will favor the production of something. Usually the production of the products, right? In this case, if we continue to heat the globe, chemical dynamics will change, right, for our different processes, and that is not a good thing. Not at all, right? So we can look at all these different things, and this is why Le Chatelier's principle is really important, right? So you have to look at it from the context of temperature, concentration, and pressure, right? So it's all there. So we have yet another lovely question. Lovely sets of questions here, right? So the classic nitrous oxide questions, right? These questions, very common, right? So consider 2N2O5 gas, right, in equilibrium to form 4NO2 gas plus oxygen gas, right? What will happen to the equilibrium position if the volume of the container is decreased? And justify your answer using Le Chatelier's principle. So as I said, you guys can attempt all the questions here, but we're only going to be doing question 1. Go ahead. I want to hear somebody. There's no calculation here, so I should be hearing answers now. Alright? Or if you guys want to take, a little bit of time to think about it. But any ideas so far? How would you attempt this question one?
Just an attempt. I would say
You would say
based on the equation, I would say like the arrow would move to the what is right because we have 4 oxygen to the on the product side, whereas we have 10 on the reactant side.
Interesting. That is not how we look at it, but it's interesting. You said it's an attempt, and it was very much an attempt. Lovely. Thank you for responding. All right. So I have 1 attempt so far. Anybody else? This is not the time to buck and shuffle and hide, right? Just answer the question if you can, right? In any way you can. Give me the answer you think is the right answer. And then we'll get the answer eventually.
Okay, I will attempt it as well. Okay, what I think it is that since the volume decreases, the equilibrium will shift to the side that has more volume, if that makes sense.
Hold on. What is this top? Which other topic is the question 1 hinting to? Isn't this the kinetic theory? Which gas law is this? As volume decreases, the pressure increases, right? So you are most definitely on the right track. But which gas law is that? Before you continue.
I think it's Charles' law.
You think? Okay, so you think it's Charles' law. Is it Charles' law? You might want to do a quick Google to confirm. Alright, but you can continue, man. So you know that the pressure is increasing. Go ahead.
Okay, since the pressure increases on one side, it will have like imbalance in equilibrium. So to become to become like stable, it will shift to the side that has more to
what would
cancel out the increase. Like, I can't explain it properly.
I get what you're saying, but the terms, key terms. So it's not that you make it more stable, but to restore the equilibrium, right? Or something like that. You could say that. To restore equilibrium, the equilibrium position will shift to the left in favor of the least amount of moles. Right? Why is it doing this? Because the Chatelier's principle states that if there is any difference within the equilibrium or obstruction in the equilibrium, right, the reaction itself will take all precautions to maintain the equilibrium itself, to restore the equilibrium, right? So we're basically talking about that. So the first thing in this question is to realize that this is gas laws, right? So the volume decreases, therefore pressure increases, and then the pressure increase, you will know that the equilibrium position will move to favor the least amount of moles, right? The first person who spoke about oxygen, right? So we're not looking at individual things. We're not looking at the individual things. We're looking at the fact that this is 4 moles here, and this is 1 mole here, and this is 2 mole here. So this is 2 mole versus what? 5 mole. So we're going to favor the least amount of moles. Everybody see that? Everybody sees that?
Yes, sir.
Right? So it's just something like that. So you're going to get questions like that, and I think this compound specifically, number one, is on some past papers, right? Ammonia will definitely be something that you might speak about this year, right? So the production of ammonia, alright, probably not the process itself, but the Haber process is important, and your syllabus asks you to hint at the contact process, which is the production of sulfuric acid, but I've never seen it actually be done by a Unit 1 teacher, so I guess the syllabus just says stuff and the papers don't really reflect it, but I guess so. So the value of the equilibrium constant now. Concentration of the products. This is too small. What was I thinking? Give me a second. What was it? No. No. Here, my text box back down. Alright. Why are the words not just... Do what you need to do, people. Do what you need to do. Come on now. This is rather annoying. Alright. Okay, big enough. Alright. So, we're gonna act like that never happened and move on. So, concentration of products or reactants. Changing the concentrations of products or reactants at equilibrium, affects the equilibrium constant. According to Le Chatelet's principle, if the concentration of products is increased or the concentration of reactants is decreased, the equilibrium will shift towards the products to counteract the change. Conversely, if the concentration of the products is decreased or the concentration of the reactants is increased, the equilibrium will shift towards the reactants. Notice that these slides are giving you all the information you need in bullet points, right? However, the value of K remains constant at a given temperature regardless of the change in concentration. Interesting, right? That's rather interesting. Pressure, right? For reactions involving gases, changes in pressure can affect the equilibrium constant. So if the total pressure is increased, the equilibrium will shift to the side with fewer moles of gas to reduce pressure. Conversely, if pressure is decreased, right, the equilibrium will shift to the side with more moles, right, to increase the pressure in the system. However, the value of K is not directly affected by the changes in pressure as long as the volume remains constant. Interesting. So it's just a bunch of facts. Alright, so it's interesting to look how they change, but how the value of K remains constant under these specific conditions. Right, so concentration can change but remain constant under temperature. Pressure can change but remains constant under the volume. Alright? Let's look at temperature. Temperature can affect the equilibrium constant. For an exothermic reaction, increasing the temperature will decrease the equilibrium constant. And for an endothermic reaction, increasing the temperature will increase the equilibrium constant, vice versa. Right? So if you start to increase the temperature, alright, not increase temperature, decrease the temperature for exothermic reaction, right, it actually increase constant, right, the constant K, right, and if you start to actually decrease the temperature for an endothermic reaction, it will actually affect the constant K in the same way, right? Will actually decrease it. Okay, so this is because increasing the temperature favors the reaction that absorbs heat, endothermic, and vice versa. Right? So it's basically saying if you already have a very hot solution, right, increasing the temperature of the solution is not gonna make much sense. It's gonna be reducing your equilibrium constant, meaning that your solution is more and more out of equilibrium in that type of way, right? And if you have a very cold solution, decreasing the temperature even more won't affect the rate constant positively, right? So we're just looking at how things can affect the rate constant per se. The presence of a catalyst. The catalysts do not affect the value of the equilibrium constants, right? The catalyst will accelerate the rate of both the forward and reverse reactions equally, allowing the system to reach equilibrium more quickly. So it actually doesn't affect K at all. At all. And when we talk about K, we're talking about Kc and Kp, right? It doesn't really affect anything at all. Catalysts don't really do anything, right? Other than increase the rate of reaction, right? Via an alternative pathway. So looking at this now, if K is greater than 1, then the equilibrium favors the products, indicating the forward reaction predominates. Right? If K is less than 1, then the equilibrium favors the reactants, indicating that the reverse reaction predominates. Right? If K is equal to 1, the concentration of products and reactants are roughly equal, suggesting that both forward and reverse reactions proceed at similar rates and the system is at equilibrium. Everything makes sense so far, guys? Just drop a 1 in the chat. Just drop a 1 in the chat if you've been listening, if you've understood everything. If you have a question, just ask a question. If you do have a question, just ask your question now. So you can ask questions. So if you have a question about concentration, pressure, temperature, the catalyst, or the values of K here, you can just ask it. Free to answer them now. Alright. So if K is greater than 1, you know products will favor. If K is less than 1, we'll favor the reactant. If K is equal to 1, magically it's at equilibrium because it's equal to 1. Interesting. So if Kc is equal to 1 or your Kp is equal to 1, your system is at equilibrium. And note that majority of the time it will never be equal to 1. In your case, it will most definitely not equal 1 in most of the cases. Might be on your exam it equal 1 and them ask you to tell you what happened and then you forget to say that the system is at equilibrium. I don't know. But just remember these interesting things, okay? So what can Kc tell us? The direction of the reaction. So the Kc indicates whether a reaction predominantly favors the formation of products, right? Meaning that the Kc is large, or the reactants, right? Kc is small, right? Or has sufficient amounts of both at equilibrium, which means close to 1. Right, so it's really close to 1, not necessarily equal, but close to 1. Right, the reaction yield, it can tell you how much you're going to get. Right, so that's important. So Kc values correspond to higher yields of products at equilibrium, while lower Kc values indicate lower yields. Right. The reaction quotient comparison, we're going to look at the reaction quotient, by the way, to Kc, helps determine the direction of the reaction that the reaction would proceed in, right, to reach equilibrium. So if Q is less than Kc, right, reverse if Q is greater than Kc, right, and at equilibrium if Q is equal to Kc. And then we look at temperature dependence and comparing different reactions. So all this information is here for you guys, alright? Should be no problem. Right, I noticed that I included the Van 't Hoff equation. You guys don't need to know that, right? But the last thing we're going to look at here is Q, and then we will be over with this entire topic. All right, just bear with me for a few more moments and we'll get through this. Okay, any issues so far? Any issues so far? Alright, in the interest of time, let's move to reaction quotient. To find the reaction quotient Q, you need to determine the concentration of the reactants and products involved in the chemical reaction at any given point in time, regardless of whether the reaction has reached equilibrium. The reaction quotient is calculated using the same formula as Kc, but it is based on the concentration of the reactants and products at a specific point in the reaction rather than an equilibrium. Right? So in other words, reaction quotient Q is Kc when it's not at equilibrium. Right? It's calculated the exact same way, right, when it's not at equilibrium. Okay? Make sense? Everybody good? Makes sense, right? Hello? Are you guys fine?
Yeah.
Okay. So if you calculate, or you try to calculate Kc when the reaction is not at equilibrium, then you actually didn't calculate Kc, you calculated Q, right? The reaction quotient. So it's important to know that you have to always check your questions to figure out whether or not your reaction is at equilibrium. Right? So you're going to do all of that, right? So to find the concentration of the substances involved, you can use experimental data if available, or calculate them based on the initial amounts of reactants and products and the stoichiometry of the reaction. Be sure to consider any changes in concentration that may occur due to the progress of the reaction, right? So which already spoke about what happened, the relationship between Kc and Q in this slide already, right? So let's talk about this. They're talking about how you find the concentrations overall, right? What are you gonna do? How are you gonna find it? Using initial amounts of reactants and products and stuff like that, and then using stoichiometry to figure it out? What do they mean by that? What they meant was ice tables, right? Have you guys done an ice table before? No, what do you mean by no? Oh my. This is a chemist's best friend, especially when it comes to equilibria. So an ice table, initial change equilibrium table, is a simple matrix, right? Formalism that is used, right, to simplify the calculations in reversible equilibrium reactions, right? So I stands for the initial concentration, C stands for the change in concentration, and E stands for the equilibrium concentration. Alright? This is your last surprise of the night. Your last birthday gift, your last Christmas gift, I don't know, your last goodbye for tonight. Alright? So, for the persons who haven't done an ice table, crazy stuff. Right? It says use an ice table to determine the equilibrium constant Kc for the following balanced general equation, or general reaction rather. The data provided is that a sample consisting 0.500 moles of X is placed into a system of volume 0.750 liters. At equilibrium, the amount of sample X is known to be 0.350 moles. That is all you need to find Kc. Interesting stuff. Initial concentration, change in concentration, and equilibrium concentration. Right? So I do these sessions with the assumption mostly that we have done the topics before, because we would have been doing chemistry since September. So you guys have gone across these topics already, because a lot of teachers start with module 2. And if you started with module 1 already, that means that you reached module 2 already. So we'd assume that you'd have done this already. So I'm going to give you guys some time to do it. Question, anybody here has attempted ice tables before? Have done ice tables before?
No, sir.
No? What is happening? Alright. Okay, so is it that I should just do it?
Yes.
Because ice table was on 2021 exam, and I think it was on 2022 as well. And it was probably on 2023's exam, right? So who's to tell? 2024 might be a nice, pretty ice table. And they won't give you the table. They'll give you the question, and you're gonna sit down, picking what you hear, trying to figure out where you get the Kc from when you actually needed to use an ice table. it's a method, so it's not gonna be part of the question. So it's not gonna come in like use an ice tip. It's not gonna tell you that. It's gonna give you a bag of information, one big whole paragraph, right? Nothing to do with chemistry, one big whole paragraph, and then you have to figure out whether or not you need to use an ice table. So let's look at this. Let's figure this out together. Let me get a page. So this is going to be a long process because it is a long process. So the ice table, right? So we're starting off with that. What do we start off with? Okay, let me write it down actually. So 2x. Okay, and then 0.500 moles there out of volume of that. All right, this is actually fine. This is lovely actually. It's an easier set of questions, I would guess. All right, so let's start with the equation itself. All right, so Kc itself, we know what Kc would be overall, right? We don't care about Kc right now because we can't actually get the answer anyways, right? We need the concentrations. Okay, so let's do initial. Why is my pen not penning? Are you guys seeing writing on the screen?
No, sir.
Crazy stuff. Let me get this thing, man. Are you telling me that before I reach a complex equation, my pen just stopped penning? Okay, so I think it started penning again. So initial change in concentration, and then you have equilibrium concentration. Alright, so what we said, we said initially, all right, we have a sample in which, let's write this 2x. We have 2x, we have 3y, and we have, and we also have 4z, right? We said that our sample of 2x contain 0.5 moles. All right, so 0.5 moles, okay? And that this is the actual reactant. So initially these would be 0. Make sense? Make sense so far, guys?
Yes, sir.
All right. We also have a given in the question again. We were also given that the equilibrium concentration of 2x is actually 0.35 moles. All right, remember that all of this is moles. All right, so 0.35 moles. So we have that as well. Okay, so what we're saying is that this must be something. This must be something. Oh, sorry about that. Don't know what's happening with that thing here. All right. Question: will the reactants increase the farm products or decrease the farm products? Will the number of moles of reactants increase or decrease the farm products?
Decrease.
Decrease, right? So it decreased by an x value, right? And that means that these two will increase by an x value, right? Right? A specific x value. But we have to look at the stoichiometry of the entire thing. We have 2x, 3y, and 4z, right? So we're gonna have to look at this entire thing, right? So 2x is decreasing by negative x, right? So it's a value, right? But we can actually figure out the change, because if we initially have 0.5 and at the end we have 0.35, what was the change there?
0.15.
0.15, lovely. not me writing 0.5. 0.15 change, right? So we can figure out now. So if we look at the stoichiometry, 2 to 3, this would change by 1.5x. And this would change by 2x. This thing keep on switching. I'm so sorry, guys. This would change by 2x. Oh boy. Makes sense, right?
So where we get the 1.5 from?
Because 2 times 1.5 is 3. And 2 times 2 is 4.
Oh, that makes sense. Sir.
It's a stoichiometry, right? Because it's just like what would I say? No, balancing an equation in a sense, right? Or mole ratio. It is mole ratio. It is actually mole ratio, right? So we're trying to figure out that. So we're looking at the ratios. We're looking at the number of moles here, right? So if something 2 moles of X decrease by 0.5, right? We're looking at the fact that 3 moles of Y have to increase stoichiometrically and 4 moles of Z have to increase stoichiometrically as well. Right? So what we're saying is that if 2x decrease by X amount of value, right, then 3y have to increase stoichiometrically and 4z have to increase stoichiometrically as well. So that's why we take into consideration stoichiometry. Are there any questions? And I'm doing it step by step, taking my time, right? Are there any issues yet? I don't hear any issues. So what is 3y changing by now? Or what is it? Yeah, what is the x value? What is 3y changing by now?
1.5?
It's not going to be 1.5, alright? What we're saying is that, remember, x was 0.15, right? So we're looking at that. So if we decrease by 0.15 here, right, we have to increase stoichiometrically going across, right? So if we decrease by 0.152x here, we're going to have to increase by 1.5, right, times 0.15, right? So 1.5 times 0.15 would be 0.225. So it'd be increasing by 0.225. Let me put that 0.225. Right? And then if we just times it by 2 over here, because it's actually 2 to 4, right? So it's a 1 to 2 ratio. We times it by 2, right? We have 0.3 actually over here. Can everybody see that and appreciate that?
Yes, sir.
All right. And if that is a change, right? So if they change by that from 0, their equilibrium concentrations will generally be the same. So these will just come down. I don't know why it's changing the screen all the time. It just wants everything to end. Right? But this is what's happening here. So we end up with these equilibrium amounts. Right? So we're working with moles here. So let me just drop in the mole, because that is what we were given, moles. Right? Are there any questions though while I do this? Any questions? It is a chemistry method that you will, I'm not asking, you will have to use. So if you have a question, ask a question. Alright? So that's basically it for the first part. Finding the equilibrium amounts for all of them, right? So with these equilibrium amounts, then we can find the concentrations, and then we can find the Kc. Right? So at equilibrium, 0.35 moles of 2x existed, right? 0.225 moles of 3y exists, and 0.3 moles of 4z exists, right? The question did state that it is all in the volume. V is equal to 0. This is from the question, by the way. I didn't drag this out of nowhere. Liters. And you can just use liters, it will be fine. Mole per liter is still mole per dm cube, in a sense. Right? In a sense. Notice what I said, in a sense. So you can still use mole per liter in this case. Right? So using this now, you can find the concentrations and then find Kc. Not true? Isn't that true?
Yes, sir.
Alright. So the volume is there. And concentration is number of moles over volume. So all you have to do now is divide all the equilibrium moles, right, by 0.750, right, to get your molarities, and then plug them into the equation, and then you can get Kc. Do I have to do all of that, or everybody's fine? Because if you understand to here, you're good. Because all you have to do now is just do more extra math to get your Kc, which should be 3.17 times 10 to the negative third power. Let me just repeat that. Your Kc should be 3.17 times 10 to the negative third power. So if you're gonna finish the question and you don't get that answer, your answer is wrong. Alright? So that's basically it. Are there any questions though about the entire topic?
Nothing.
Alright. It seems as if my job here is done.